Good morning, everybody. This is Fred Schaeffer, and thanks for joining today's Ascendo Reliability webinar. And as the decade turned over and as the year turned over and all of those kinds of triggers occur, I did not start a new diet or workout regime or any of that kind of stuff, but I did have the chance to see a lot of, the decade in review or the top news stories and a lot of that kind of stuff over the last couple of weeks. And it got me thinking about, well, how has reliability engineering changed over uh, recent time frame? I think reliability change is slow enough that we're probably talking 30, 40 years, and with an eye towards looking out to the future a little bit. So apparently this title at least was a popular title because we ended up with quite a few registrations. So I appreciate that. And looks like we're getting a really nice turnout also. So please keep the chat window closed. We are going to use that quite often, and hopefully that we get lots of information in from you. Welcome Alberta and Mohammed and Carla, and I see a couple of names, Maharaja, I believe, and a few others that are. I should take just a quick moment and mention that a few of the names I'm recognizing are people that attend regularly, and I appreciate you coming back and joining these webinars. And also a few people are signed up for the CRE prep course. We're going to use this Adobe uh, Connect type platform to deliver that class. And there's people from all over the world. I think one of the students is from Singapore, another from Italy, a few from all over the United States. There's still a few seats left in that. It starts this afternoon. The sessions will be like these webinars will be recorded. You can find more information at ascendoreliability.com underneath the courses and look for CRE Prep Live or CRE Live Prep course. I don't remember how I titled it. Either way. But anyway, enough of the upfront advertising. Let's dive into today's topic. Now, one of the things, and I know many of you have run into this, is that we're seeing and hearing a lot more about risk management. I mean, even the ASQ Reliability Division changed their name to Reliability and Risk. And we're seeing it in standards, we're seeing it in lots of different places. But what does that really mean for us in the reliability world? Right? We'll talk a little bit about that. Now, another major area I've seen, and one of the questions that came up as we were getting ready to get started, scroll back from Ricky, asked an interesting question as well. How do you move away from being a reactive organization to being proactive? And I think you were talking, Ricky, about in a chemical plant. Well, I'm quite sure there are things already in the proactive element, sensors and warnings for pressure of vessels and so on for the operation itself. I've toured and worked with folks in chemical plants a couple of times and know that some of the reactions have to be pretty carefully monitored or controlled or they can really cause a problem, not only for poor quality products, but for safety also. It's getting that kind of mindset moved over into your maintenance program, I think was what your question was, is that challenge. Now we also see it in product design and moving from a reactive organization, waiting for something to fail or waiting for a customer to complain before you take action. I think we're moving further and further away from that phenomena. And it's a good thing. It's one of the trends I really do like. Now, the other piece of this is that we have a lot of new technology, both in the products and the systems that we're designing. But just think of the Internet of Things and all of the sensors that are becoming available, both in our systems to manufacture products, but also within the products themselves. Now, this one it's been on the horizon for years. It's gaining steam, and in my opinion, it's one of the most powerful ones. Yet has the some very significant challenges and barriers to it. And we'll talk about that a little bit more. So those are the kinds of three top trends here that I'm using just as a teaser as we dive into this thing. But let me go back to something that will become relevant a little bit later. Um, in the chat window, do you you and your organization, do you use MTBF or have you moved away from that? Now, this might not be a pleasant question to talk about early in the morning here on the west coast of California. MTBUR. So, Jay, I imagine you're in the aerospace industry of some sort. So, a lot of yeses. This is not really using it. Frederick, I appreciate that. And good name, by the way. Um, trying to move away. Good on you, John. Keep that up. If requested. Yep. And Carla, lots of customers do request it. And I think part of that is they just don't know. Struggling to move away. Scott, let me know how I can help. Um, yeah, now seeing more no's. Good. I should have actually used a poll on this one, I guess, to see how we're doing. MTBF has been a fixture in reliability since the 50s. And any of you that have seen any of my writing that's being posted on LinkedIn or in the No MTBF blog know my position on it. And I appreciate the number of you that are saying not really moving away from it, struggling to get away from it, because I've been there. I know all of these discussions and arguments and so on. Yet this is really a one just to reinforce moving away from this, and we are as an industry moving away from it. More and more standards are coming out without its use. Unfortunately, ASQ's body without its use. College still has it listed as a metric and a common metric. Unfortunately, it's a catch-22. It is a common metric, yet it's really not a useful one. So I don't know why they list it. I get comments and feedback from people directly and through the comments on the blog and on LinkedIn that companies are being successful at getting rid of it and moving on and explaining and using something different. So that's one piece of evidence that our industry does change. We're not saddled with just because that's the way we always do it. Let's use that by extension to lots of the other things that we do. But first, let's start with going back a little bit, right? The basic concept of reliability is that it should just work. Now, this gets muddled with availability, with dependability, with ruggedness, with durability, all these other ilities and all kinds of other things. But way back, if we go use the Wayback Machine and go back to the 1700s and your local craftsman was making a cabinet for you, if it collapsed after 2 days of use, you know where he lived. You know where to take the parts and say, hey, fix it, make it right. You also would probably not purchase another cabinet from that person. You usually knew the people making the products for you if you didn't make them yourself. As we got more, cities got larger and as people became more specialized, you may not know them very well, but there wasn't a lot of competition available. So you dealt with the local quality you had, and if you wanted something better, you sought out a better solution. But the term reliability really wasn't used. There's either it functioned, it worked, or it didn't. And those failures were still discussed. There weren't mandated warranty periods and all those other things. Yet a reputable craftsman would make it right, would do their best to make it right. And those people tended to stay in business. It was a natural cycle of how this concept of reliability works. Now, some of you may have heard of the one-hoss shay, which is a one-horse carriage, and it has two wheels and traces that go out to the horse. And there's a poem that was published in the Atlantic Monthly. Oh, when was that? In the 1850s time frame, and it basically talked about this parson uh, uh, um, or deacon, I think it was, that was upset that a one part of his carriage would fail, then another part would fail, another part would fail. So he set out to build one that had every part as strong and as every other part. And the idea was to prioritize what was most likely to fail. And he mentions that the axle, a connection would fail, is most likely to fail. So it made a much, much stronger uh, axle, use the best wood and the best craftsmanship and the best metal, use the on and made that as strong as possible. And then it should in the best fail is most do another piece and then another piece and another piece. And each one was made as strong as the others. And you can see what happened then is that you can see the other piece. The end of well, I won't spoil the ending if you haven't read this, but it was really a lot of different concepts around reliability engineering that got built in to this discussion. And they were into that poem. And that was in the mid 1800s. Right now, we fast forward a little bit, and we're kind of in the realm of more complex systems. Aircraft were being made for the war effort in the 1930s and 40s. War effort in the and that was in larger ships, more complicated communication devices, more prevalence of consumer products on automobiles in the early 1900s and mid 1900s. And at some point, we finally decided as a society to define reliability in an engineering way, right? And this is the one that many of us know. It has four elements. There's the probability and duration, or two of them, right? Probably, and then that it should. What are the how do we define failure? What's its required function? What should it do without failure? And that might be the axle doesn't break, or the seat doesn't crack, or the paint on your car doesn't peel. It could be all kinds of different things that we define failures as, but we need to be specific about it. And then over some period of time and in conditions, or I should say conditions, environment. It's both the weather and how people use it. And so we kind of came up with this formal definition, but let me ask this. Is this the way your customers define it? And if not, how do they define reliability? Or the seat? Yeah, Micah, you better not use MTBF. Um, and keep that in mind when you interview with companies. And for those that don't know, Micah is my daughter. I believe it's the same Micah. Um, and is just entering the workforce. So hopefully MTBF doesn't show up for her. Tried to make that happen. I saw a bunch of people typing. Oh, I see what happened. My window's not scrolling. Part of the NPI process, management moving toward it, contractors. Oh, there's more MTBF stuff. Oliver Wendell Holmes. You're right, Andrew. That's the one Hache. That's what we use. Average calls per year, car companies. Right, I'm still trying to catch up. Availability needs to work for a long time. Return rates. Yep, consumer electric typically don't think about. You know, Samuel, I used to work for Hewlett Packard and in the inkjet printer business, and one of the occasions was to for a launch of a new product we had, where some of the engineers were asked to go to local electronics retail stores and observe how people selected printers and answer any questions. We were obviously identified as HP people, and I thought it was rather brave of them to let reliability folks and engineers in general go talk to customers. Uh, One customer said they were looking at a couple different printers and boxes. She was looking at HP printers in particular and saw me standing there and said, "Hey, could you help me pick out the right printer?" I said, "Sure. How do you plan on using it?" And he goes, "Well, I pretty much know I want this model, six model 600, but there's six boxes here. Which one of those six boxes will work for 4 years without failure?" And I'm thinking, I have no idea how to answer that question, right? Um, but she wanted one that she wouldn't have to go back to the store and buy another one because the one she had failed. And now she's back to the store again, and she didn't like that process. And so I disagree that consumers don't think about reliability. You certainly think about it when it doesn't work. If your phone doesn't take a charge anymore, that's a failure, and you probably are concerned with that. And then probably consider it to the extent you can. There's not a lot of information available of, well, how do I deal with that? But the definition came out no, in the 1950s, I believe, that it became a formal thing, and it was through, I believe, a military standard initially, and then Pat O'Connor and other authors have coded it based on those earliest documents, and it's essentially a common one. But the key point here is most of our customers don't use the same definition we do. And most of the engineers and managers that we work with also don't use the same definition. And so even though that we've defined it and can rattle off the four elements pretty easily, it's not common. Most engineers I've worked with, other than reliability and quality engineers, think of it as it should not fail. But they don't really think, or they say it's a 5-year product. Well, it's only a duration. Well, what's the probability part? Or they'll say, well, it should be highly reliable. Well, what do you consider highly reliable? It's at 5 nines probability, but over what duration? And so on. It, and then the worst are the ones that just give it an MTBF value. Really don't know what they're talking about. So lots of variations in that. What the definition of reliability did and the advent of all these tools that we use, right? I use 3-letter acronyms and 4-letter acronyms on the side here. Um, and there's dozens and dozens of other tools and techniques. I once asked a colleague, if I was considering all of the various tools, I was working on a manual, basically, a checklist, and he came back with 148 specific different tools, everything from sneak circuit analysis to material degradation testing, and I mean, all kinds of weird stuff, and a lot of the common ones. But the advent of the definition and these tools that came about because we were trying to figure out how to get better at designing and building and responding to failures when they occur. How do we build a better product, and how do we respond to failures more efficiently? And many of the tools we use today, the fundamentals of them were built in the 50s and 60s, usually on large military projects. I think there's submarine projects in the US created a bunch of projects like reliability block diagrams. And I think FMEA started based on an aircraft system in the 40s. There's been all kinds of them. But the idea is that these tools and techniques have been around for quite a long time, right? And there's always these new innovations of how to do ALT or block diagramming or Markov analysis or whichever technique or whatever there is. There's every year at the conference, um, there's all these different ways to squeeze a little bit more out of what these tools are capable of and can do. But fundamentally, the ones that we use day in and day out really haven't changed a whole lot. Um, I did get a question yesterday from a person that's listening to the Speaking of Reliability podcast without. Well, I did get a without your podcasts are great and they talk about all these great tools, but how do I know which one to pick when? Right? We have too many tools was kind of the comment, and how do I know which one to use that's effective for this particular problem? Now it's an interesting question and probably going to be a subject for a lot more discussion. But it's true, right? And even if you pick accelerated life testing, I mean, I've done a number of different webinars and written about it at length, that there's many different ways to go about doing accelerated testing and different flavors of it, right? And so we've got tools. There's no doubt about it. The pace of fundamentally new tools has really changed. We're not seeing a completely different way to do risk analysis, for example. We have FMEAs and HALT and um, fault tree analysis. are fundamental ones. And then there's a handful of other tools that are coming about because of the technology we have available, but they still rely on these older tools to organize them and sort them. So in your world, what it, what's the latest? What's the most current innovation that you use? What would you say is the most recent invented tool that you probably use? Weibull analysis. Weibull analysis has been around since the 50s. Fault tree analysis, I believe that's from the 60s. Uh, Reliability growth analysis. That one's not that old, but I know I believe it's from the 70s. Cause mapping. Mark, that one's, I know I saw that in like the 80s, so that's pretty recent. Now, Apollo root cause analysis, Zach, is root cause analysis. We've been doing that for centuries. Apollo has a nice new spin on it, a nice take on it. That's not that old. Yeah, Crow AMSA for the growth. It's not too old. Database FMEA. Yeah, good one, Karen, because that's enabled by the computing power we have available these days. I have an opinion on whether that's useful or not, but it's a way to think about it. A lot of the modeling techniques, like um, physics of failure, a lot of that is enhanced by the computing power we have these days. But remember that physics of failure was first used and invented essentially back in the early 60s. It just was very difficult to do without the computing power to assist. So we'll talk some more about physics of failure. Innovation is not a tool, but the overall approach to have the culture implemented. Good one, Louise. I know I've been writing about it, and there's a standard out there now, especially in the electronics industry, that talks about reliability culture. The concept, I mean, where I write about it and where I pulled it from was from Quality is Free. From I think Phil Crosby wrote that in the 80s, and he talks about the quality culture, which is a very synonymous with the reliability culture. Yeah. Okay. Good. Good list of tools out there, but I think vast majority of these, with a few exceptions, have a long history, and we've been using them for quite a while. The use of computers, by and large, is a bit new. Now let's take a look at some of the trends affecting us in a more general way. I think all of you have seen a trade journal article that says customers expect their products to show up sooner or more often and be less expensive and have more functions and be better, just faster, cheaper, better. All of those criteria for product development is continued. The automotive design cycle is trying to get to be less than a year. It used to be 4 or 5 years, right? Cell phones, they come out every year. Now, the pace of innovation in them, we could argue, is slowed, yet we keep getting bigger and better batteries, we get more bright screens, we get all these other features and capability and speed. We're seeing the advent of more and more voice controlled activities, kind of harkening to the Star Trek computer on their ships, being able to answer questions for you, those kinds of things. That takes a lot of computing power to make happen. Um, Customers are, I mean, there was an article which in part prompted this topic a couple of weeks ago in, or more than that, but a while ago, uh, that one of the tech writers at the Wall Street Journal decided to use 1910 technology for a day. So she traded out her smartphone for a flip phone. I think the initial iPhone was in 2010, and even with that one, it didn't have near the capability that today's phones have. And it went on and on and on. Of all of the things that were not available 10 years ago. And it was a fascinating read because just about every facet of her life, now realizing it was an article pointing out the innovations in the last 10 years, but it was staggering. And Some of those innovations are not demanded by customers. And Steve Jobs is famous for, doing development work for creating products that we didn't know we needed, kind of thing, and then making those work. And plenty of ideas didn't pan out. But the idea is that as soon as you get a phone and you run into a limitation, or you open a website and it's difficult to navigate, or whatever, you now have some tension to create something better. And either you let the manufacturer or the designer know, hey, could you make it better? Or you do it yourself, or you go find another solution. This hasn't changed, right? When I was working with product development 30 years ago, it was faster, better, cheaper. It was in the trade journals, and it just is today and as ever. It's become trite to say that this is getting more prevalent because it always is, right? This hasn't changed at all. Customers want product like your car. My dad would trade in his car every 2 to 3 years because he didn't like the idea that it wouldn't work and that the cost of maintenance would continue to go up after that period of time. And this was in the 60s. Today, you can buy a car and it will likely last you with minimal maintenance for 10 years easily and maybe longer, right? We expect more, and that continues in every industry, every kind of product you can think of. The other piece of this is that something that wasn't really prevalent 20 years ago is review sites. Amazon, you can review a product, or you can a local bakery if they don't have good customer service or their bread is not all that tasty or whatever, you can review them, right? The number of times that you're looking for, I was looking for a chimney sweep a couple months ago before we started our fireplaces here in the winter time, and I wanted the flue cleaned basically. And I didn't really have a particular one in mind, so I went online and looked, and there were a bunch of Yelp reviews. And it certainly influenced my decision. And you may run into that over and over again. Hey, Sean, 25-year-old car, make sure it has seat belts. It probably does. Um, the idea is that it's not just warranty anymore, right? It's not that the part fails and the manufacturer makes it right or replaces it, or you have a disgruntled customer, just one. That old adage of word of mouth now is amplified, right? It used to be before the internet, essentially, that a happy customer, very ecstatic customer, would tell two, three other people. As the occasion came up, I would say, "Oh, this is a great car. You really like it. It really lasts. It's really good." Or this dealership or this bakery were really good. You should try it out. We as humans are much more prone to warn other people. That bakery is terrible. The bread was stale. It was this or whatever. You will tell 5 people that. Right now, when it's in person, and folks had studied this years ago, is that happy customers tell a friend, right? Dissatisfied customers tell 5. It could be strangers too. They will tell other people. It's much more motivated to tell people about bad experiences or bad products. With the internet, and Yelp I'm using as an example, that gets amplified. You can post a review and it could be seen by thousands, right? Think of the Samsung folding phone that came out or almost came out last year. I don't know if they actually ever introduced it. They sent it out as a common technique for marketing and sent it out for reviews to various tech writers. And it failed pretty darn quick, right? And the reviews were written saying, nah, it's not quite there yet. It failed. I have a review for part of this product and this and this and this and it was in the news at all of these bad reviews and it got pulled back. Other types of examples are, um, oh, I don't remember what brand it was. A phone's battery caught on fire in an airplane. Right? I don't know if they were in the air or not. I don't think so. But very quickly, airlines banned that brand or that particular model of phone from the airplane, from from traveling it by air. Now, for business travelers that owned that phone, that was a real inconvenience. They weren't allowed to bring that phone onto the plane with them or bring it with them. Uh, that got publicized. That got moved out all across the internet and on national news. Now, the internet just amplifies this stuff. So if you have a poor performing product or a product that has got um, unique or a higher failure rate than others, it's not just your customers that know this. And even in the old days, individual customers may not know what the overall rate is. They know their own experience. Now, not last year, it's widely available information that anybody can look for. Now, it's prone to errors and all kinds of issues with it and all this other stuff, but it's still out there. So when a failure occurs these days, it's way more expensive because it can cost you lost sales, which they never were a customer, we don't know why in many, many cases, unless you're tracking all the social media stuff. Yeah, the Note 7, I think that you're right, Sam. It, I guess they're pushing the edge of technology and they keep running into problems, but they seem to be surviving just fine. But it's expensive. That's the bottom line of this, right? Supply chains, another huge factor for us, and it's not only that we buy parts from and components from and manufactured components from all over the world, is that because of the tariffs and the volatility of the political environment, our supply chains are getting way more complex, right? If you're sourcing material that's being hit by one of these tariffs over the last couple of years, you're scrambling looking for other sources. You're looking for cost relevant options and so on. It changes the complexity of your supply chain, and the risks of supply chain disruptions is continuing. And it's going to be, I use Ford's Motor Company in the early days, as they had their own iron mines, they had their own shipping company, they had their own forests, they had mills, they brought in raw materials and made a car. Unless you're in the raw material business, right? Drilling for oil or digging up iron, you probably don't have that capability within your product. Most products these days rely on suppliers, which then rely on other suppliers and fabricators, and then source material folks to create their products. The question though is well, how deep do you go, right? I remember I had a problem at Hewlett Packard once that dealt with the electrolytic capacitor. And we typically bought from manufacturers of electrolytic capacitors. But that capacitor vendor bought components from chemical companies that would then be mixed and put into the capacitor. And it was a supplier to one of those suppliers. It was like 4 levels down or away from our purchase, that a change in the filter of a flame retardant, for example, changed and it caused products to fail. Or a change in the formula of an electrolytic solution at a supplier to suppliers and so on, that caused problems to occur. Now, when we vet and work with suppliers, well, how far down in that program do you go? Yeah, and you're exactly right, Mark. Dr. Peck's certainly been talking about this. You need to know not only that do they make the right form, fit, and function with the right capacitance, but is their process stable? Are they vetting their suppliers, and so on down the line? The auto industry even codified this years ago, and made it an obligation that each manufacturer fully understand the technology and risks associated with what they're buying, and then impose that on the suppliers at the next level. And so, in theory, if everybody does their job, there's not going to be any issues. Well, we kind of know that's not happening. In in a real practical way, I worked with an inductor manufacturer that said inductors are used in everything electronics. They're almost on every component, every product out there. We have no idea how it's being designed into the product, We have some idea, but we don't know exactly. We also don't know the range of environments they're being put in. We keep getting surprised of where these things are showing up. They can't keep up. We're just too darn innovative, I think was what they were saying. So what do you see? Those are the big trends affecting us. Supply chain, uh, the cost of failures and the speed of that information getting out. And well, I drew a completely blank on what the first one was. Let me take a look. What are you seeing? Oh, customers demanding more. That one's just a constant. Yeah, good one. Good way to put it, Michael. Yeah, I like that. Supplier audits, remember the ISO 9000 series was an idea to get rid of having to do audits. If you met that criteria, they were good. I don't think that was ever really adopted. Or a lot of people are ISO certified, but that's just a starting point. Um, it means they do what they say they do. It doesn't mean they're any good for your application. Cycle time reducing. Yep, definitely. Big data. Yeah, yeah, and I'm certainly going to talk about that. And it's not just, I would say big data, but more data. And we've always had lots of data. I think there's some other innovations there that are coming up. Yeah. Ooh, customers attaching penalties. IBM has been doing that for years and years and years. If you have a power supply to a server for IBM and that power supply fails, they charge you for the loss of the entire server, not just the replacement for the power supply. It's one way they build it into their contracts. Oh, good. These are all good. All right, great. There's a lot happening. Right. Some of the recent changes, and I'll cover this fairly quickly, that I see is happening that's affecting reliability in particular, a little bit more directly. Um, Education has changed. When I first got hired into Raychem 25, 30 years ago, um, I was one of the few that wasn't from MIT. The founder was from MIT and had a predilection to hire people from his alma mater. It was just what they did. If you had an MIT on your resume, you probably got an interview, and if you're decent at all, you got hired, right? It was what school you went to that mattered. Now, top universities still do, like Harvard and the Ivy League stuff in the law fields. It depends on what school you got to where you're being recruited. If you go to this school for this discipline, it opens doors for you. That I don't think has really changed dramatically. But one of the things that's happening more and more, and I see more and more evidence of it in the last couple of years, is that a college education it isn't the enabler that it used to be, right? It it's more what you do. And I've seen this with the CRE certification, and I talk about it in the course at length, is that getting the certification is great. It helps you to demonstrate that you've mastered the material in the body of knowledge. It doesn't mean that you know how to use it, right? And what a employer wants is your ability to get results. And but we're seeing this change in education where people can take classes from um, MIT, for example. I think it was one of the first big universities that started doing this. And now there's hundreds and hundreds of university courses, if not thousands of courses available online for free. All you have to do is do the work, right? It's not good enough just to listen to the lecture and let it pass by you. Is do the work, read the books, do the homework, do the assignments. You can learn a lot for free these days, right? Now, one of the barriers in that is that unless you pay a little bit of money, and it's not usually much, you won't get a certificate. But what's the real value is that you have that knowledge. You can apply it to solve problems. That's what makes a difference. Um, the way people are learning these days is often they Google it. In survey after survey and discussion after discussion of why people come to Ascendo Reliability, the vast majority of folks coming are trying to learn just enough to solve the problem on their desk right now, right? So if it's, oh, I've got this, set of data. How do I deal with censored data? What's the right way to set that up in my analysis? Well, you can Google Weibull analysis censoring, and then hopefully it shows up with an article or two from Ascendo, and there's a short tutorial that talks about it directly, right? That's the vast majority of traffic to the site. Now there's others like these, like you coming to the webinars, that's more built into your product, your professional development. And hopefully you pick up a few ideas and concepts along the way, but it's in lieu of going to a conference or in addition to going to a conference. A lot of the webinars and the idea for this webinar is an ongoing conference kind of idea. But the where we get our education is changing, and the value of open courses and certifications and the ability to solve problems by learning just what you need just when you need it is becoming more and more sought after, not the MIT graduation or on your resume. Sensors. Now, I think every single one of you have got sensors in and around your factory, your plant, your production facilities, and some of you probably have it built into your products. If you pick up your phone, there's more than one sensor in there. There's accelerometers, there's GPSs, there's temperature sensors, moisture sensors. There's all kinds of weird stuff in there. If you have a smart watch, right, it might even might have the capability to monitor your heart rate and your sleep patterns. We can measure and monitor all kinds of things. Years ago, the inkjet printers, we knew that one way to speed up the rate of printing was to not assume that you were in a humid environment. Because if you were in South Florida or in Singapore outside or without an air conditioned building, you had relatively high humidity a good part of the time. And so the ink doesn't dry as fast, right? So we went to sensor conferences and we started talking to vendors about humidity sensors. And at that time, they were really only made for HVAC systems, air conditioning systems for buildings, heating and air conditioning. And they were huge. They're great big chunky devices, and the technology could be made smaller, but it wasn't because that wasn't their market. It didn't really matter what size it was. And the cost was dollars because in a HVAC system, a dollar was no big deal and it did the appropriate job. So HP comes along and says, if you can make them for a nickel at this size, we'll buy 1,000,000 of them. And of course, that got a lot of interest. Sensors are technologies from Hall effect sensors to location sensors to GPS sensors to electromagnetic, heat sensors, all kinds of stuff are just getting smaller, faster, better all the time. They're also being easier to use. Now, the hard part here is they all create data, right? They don't create answers. That's a problem. And I think that's one of the major trends is that we're seeing the ability to collect way more data, which wasn't really a problem in the past. We have more data than we ever used. 30 years ago, we had internal computing systems that collected all this data that we rarely looked at. Now it's terabytes of data, and we still don't really manage to look at it very well. And even though there's a lot of changes in data analysis, the tools and capabilities of, say, the Reliasoft's Weibull++ program is really great compared to what it was 10 years ago. We have R software, which is free, which is an amazing language for solving statistical problems. And there's books about it, there's tutorials about it, there's all these techniques about it. We have MathCAD and Mathematica. We have tools that, I mean, I can ask my little voice assistant thing to do simple math for me. I don't even pick up a calculator anymore. My search bar on my computer does math. I mean, simple stuff, I don't even pull out the old tools anymore. I first learned how to do some mathematical form calculations with a slide rule when I was in high school. That's long gone. But some of our approaches and thinking about doing data analysis still relies on techniques that were invented before the calculator, right? If you ever heard of root sum squared, right, or mean squares, that's because that was a way to solve problems based on the equipment we had available at the time. Now that the ability to do calculus on the fly or higher order mathematics or multiple variable visualization and all kinds of exploratory stuff that we're doing and manipulating huge data sets and being able to suss out patterns and trends and so on is phenomenal. Trouble is that we haven't fixed the problem of are we asking the right questions, right? Are we looking? Do we have to ask the right question before we gather the data, before we analyze the data? And it's a cyclic process, right? We look at some data and we go, would have been better if we had this piece of information. Let's go get that data. Or we needed more resolution, or we need this. It's an ongoing continuous improvement, but it starts with asking the right questions to start with. What are we going to do with this data when we get it? What problem are we trying to solve? Right. So what other changes are you seeing? I talked about data analysis, sensors, and education. What else is changing in our world uh, that is influencing what we do today? I don't know why my chat window's not scrolling today. So I'm getting behind. Yeah, more competition, regulatory, yeah, just-in-time education's act. Yeah, so I think I've got close to probably over 100 webinars now. So if there's a topic there that you want to learn more about, you can search it and pull it up and pull it up. It's changing in our world. That hour lecture or our discussion right on the spot. If you Google something, you can find a tutorial on it or a YouTube video on it. It's almost guaranteed. Good on you, Mark. Still has your old calculator. Yeah, I still have one in my desk. It's an old HP one. It'll probably work for another 20, 30, 100 years. Those things are solid. The Industry 4.0 and Internet of Things, machine learning, the artificial intelligence part is a nice innovation for analyzing data. The roots of that go back into the 70s. When I was first working in a factory, we started using um, some of the precursors to artificial intelligence, but it was really just a modeling program. And we would set up these various models, and then we use data sets to teach the precursor in how to approach those problems and solve them. Look for the correlations and the relationships in them. I'm drawing a complete blank with that was called relate. That was a long time ago. It's gotten way better, and a lot more tools have been developed in that area. Yeah, safety analysis. That's yeah, more sophisticated safety analysis. You're exactly right, David. We're seeing um, much more like a sneak circuit analysis. Doing that by hand on an electrical circuit is really difficult and time consuming. Doing it in today's world with simulations is gotten way better. The use of finite element analysis, it's built right into a lot of CAD programs. The basics of it are. And it's not as expensive and doesn't require, you still need to know what you're doing, but it doesn't require a dedicated team in 2 months to do an analysis. We can do it much, much quicker. Yeah. Regulatory and safety. Yeah, that continues to run a pace. I think, Carly, you're exactly right. Is those, I don't think those are going away. And it's a whole different discussion of whether it's appropriate or not, but it is a part of our world. More automation. Yeah. Um, and that's probably a whole discussion too, Caitlin, is, how is the automation going to affect us in the reliability world? You know, it, I'll leave it there. I think that's probably a whole topic in and of itself. But yeah, we're seeing more and more automation in our facilities and factories and so on. There's no doubt about that. And that's been for quite a while now that we're seeing robotic stuff taking over particular jobs. Um, and in many cases, it's actually very, very good. But it is making it easier for us to get consistency if we engineer the systems to be consistent in the right realms, right areas. So there's quite a bit of stuff in it, all good stuff. So let me talk briefly about some of the what I see coming up. This is why I picked crystal balls for the images for today. Prognostic health management. You know, Dr. Peck's been involved with this, and there's two different societies competing for your attention in this realm. Um, but basically, this is the process of monitoring a piece of equipment or a performance of something. And for example, a motor, and you're monitoring current draw. Now, as the is a brushed motor, and if the brushes start to wear down, the amount of current changes in order to maintain the same power coming out of this motor. And it's a known phenomena. And I'm pulling this roughly from memory, but it's the concept is that if there's something I can measure that monitors the wear out of something, I can track that for that one piece of equipment and then forecast in the appropriate range of time to say, oh, next Tuesday, it will be at some trigger point of probability of failure or not have enough capability to function. So let's replace it next Tuesday. We get the maximum life out of the product, and we get ample warning to buy spares, to align up the kit for the maintenance team to go replace that part, right? Um, I don't know how or what technology is used, but my car tells me when I need to do an oil change. And it's not based on a fixed mileage and duration. It's some other sensor that's looking when I need to do, looking at the quality or the consistency or the capability of the oil. At least that's what I understood it's doing. But that's the idea in prognostic health management. If you have a uh, something that is slow to deteriorate and you can monitor it and predict its particular line, you don't need to use the average or you need to use and saying, well, if I don't know when that brush is going to wear out, I'll replace it every 3 months, for example. And so it allows us, especially for things that are expensive and you want the most value out of that particular part, it's a great tool to do this. The barriers to this, though, is that we need to understand it at the fundamental levels. We need to understand and build those models for that particular failure mechanism in light of all the other variables that are occurring. Because if you build a model in a low humidity environment, does it apply in a high humidity environment? If it's a mechanical wear, for example, it might not. Do you know? And the hard part is running through and getting all of those different variables correct, right? So that's where this real issue comes around. So it's an interesting concept. We're seeing more and more of it being applied and talked about and discussed. It's moving out of academia, and it's the censoring part and the modeling part have the applied and talked tools available to really make it work. Now we need to look for and understand use tools like FMEA, for example, to understand what is it exactly we want to measure and monitor and build models for. What makes it what it's not difference for our product's performance over the long term, right? So this generally works with repairable systems. We should caveat that as um, but if you knew that your phone's battery was losing its capacity to hold charge and you really wanted it to last for 8 hours without charging in your normal use, there's technology available that could tell you, hey, you need to have your battery replaced because the likelihood of it meeting your day-to-day demands is going to not meet your needs anymore. And it could tell you. Now, Whether that'll actually be implemented or not, I don't know. But things like that come out of it. Now, physics of failure is not new. Dr. Beck and other authors wrote about this in a book, and it's freely available, called Reliability Growth, which is a really bad title. But it talked about kind of a bit of the history of reliability engineering and this notion of getting away from parts count prediction and other tools that we've been using ill-advisedly for decades and moving instead to physics of failure. And the idea here is that you need to understand the fundamental failure mechanisms for the technology you're using. Now, in electronics, University of Maryland and CALS, the consortium, and DFR Solutions both have software packages that look at electronics, and they dozens, if not hundreds, of different models are built right into it. So it's pretty handy. The trouble is that we keep inventing new things, right? We and it takes a lot of work to really create a meaningful, useful physics of failure model. That one of the advantages the university program has is a bunch of grad students that go off and build these models and go do the experiments and do it. If your product technology is relatively stable, it may be well worth it for you to build it for your own technology, for your own deal, and you can keep that in house. I'd love it more of those got published, but unfortunately they don't. There are models, you can build models, there's all kinds of ranges of good ways to do this. But the issue is that it's, and I think I spelled materials wrong, but the idea here is that you need a detailed model essentially of the relationship between the stresses applied to your technology and its time to failure. And for some failure mechanisms, we have wonderful models for that, and others they're a bit shaky, and others we just don't have them. And so it covers a good realm of failure mechanisms, but not all of them. And we keep inventing new stuff that need better models or new models. So it's the challenge. But I see the prognostic health management and physics of failure are both continuing to grow in interest in the capabilities we have, make them more and more requirements for what we do in reliability engineering. So if you don't already know about those tools, those are things you need to know about. The last one I want to mention is risk management. It's becoming part of the language in reliability. Like I mentioned earlier, as ASQ's changed the name of the reliability division to reliability and risk division. ISO standards are now including risk. There's a concept called enterprise risk management, right? And there's reporting structures for identifying and mitigating risks. Now, in the reliability world, we do this all the time, but not at the corporate level. But now we're being asked, this is the trend I'm seeing, is that we're being asked as the reliability folks, asked to use tools like FMEA to help identify the risks to this product in its development, which we would do anyway. But that becomes part of a risk profile and risk reporting up to senior management in their business making decisions. Now, some companies do this naturally. Others are being mandated to do it. So we're seeing more and more emphasis on risk management all through the organization, and not just for product failures, but for market trends and for business decisions and for viability of a concept and so on, is well beyond the uh, the way we applied our tools in the past generally. So I'm seeing more and more of a shift from how do I reduce the failure rate to how do I articulate the balance of the risks for our business and for our customers, which is a subtle shift, but I think we're getting more and more of that as we go forward. Getting right. So I'll leave this one here as I close out. We're coming up at the end of the hour here, and I appreciate everybody's comments. I'm having a hard time keeping up. Is my DFR stands for Design for Reliability. And yeah, PM, I'm looking at through some of these. So what do you see are the trends? What do you see that you're going to need to learn about or master or apply as you go forward? This was just my take on it. By no means is it the end of the story on it. Does oh, thanks, Sam, for answering the question. Bayesian statistics. Yeah, you're exactly right, Mario. As more and more of our capability gets there, a lot of the stats tools that have been built really don't do Bayesian statistics. Now, the other half of this is, given my experience with it, it usually means we get to use one less sample. So instead of 22 samples, you can use 21 samples. And in some places, that may be very, very useful. But other places, it does add a ability to use our prior knowledge and information in a more meaningful way. And so that's all good. And it's enabled more by our technology of data analysis tools, but it's also a shift in the way you think about your analysis. That's the hard part. And I really learned the frequentist style of statistics, so Bayesian's a little bit of magic to me in many cases. But I know it's good. Let's see, Silicon Valley, more and more specialized reliability engineers. And I agree with you. I see that where people are looking for somebody that knows just silicon fabrication reliability engineers or automotive. Silicon Valley is really getting into the autonomous vehicle space. So a lot of auto engineers um, with experience in that and then reliability. Yeah. Material science. A lot of really good reliability folks come from physics or material science or chemistry, right? Because we have a fundamental understanding of, I'm saying we because I have a physics background, and how things work and don't work, and so it's natural into that. More big data stuff, Christine. Yeah, we'd use risk management and looking into more big data. It's there's so much out there. It's a matter of what how do you look for it? How do you put it all together? But yeah, dealing with the data sets we have or have access to is more and more coming up. And we have the capability. My first computer on my desk could not handle more than, I think, a megabyte of data at any one time. I don't know what my limitation is today. I don't, and I doubt I have a data set big enough to try it. I know some of you do. Software reliability. David, excellent. Yeah, I don't, I know software's out there. I know it's a part of the system reliability. I've dabbled in it in a few areas, but usually I bring in others that are much more versed and capable of dealing with software reliability particulars. And it's just beyond the edge of what I know. I know it's important. And I agree with you that as products continue to are really software based, much more than hardware anymore, it's becoming more and more prevalent. And that's been ongoing for a while. Good point.